Okay. So my purpose today is twofold. One is to give a general pedagogical introduction, the rather mature subject of quantum spin liquids, and then tell you about uh, relatively recent work on old problem, which is understanding the pseudogap phase of the cuprates. And so before starting, I should mention my various collaborators. Yahui Zhang was a postdoc at Harvard and now is a faculty member at Johns Hopkins University. He was the one who started the line of thought that I will present on the pseudogap. Alex Nikolenko and Maria Tikhanovskaya are graduate students at Harvard. And I also collaborated on some of the work with Doug Moore and student Eric Moscott at University of Chicago. Okay, so let me begin by a very basic result in condensed matter physics, discovered, I guess, in the 1960s or 70s. It's really the foundation of everything in conventional condensed matter physics in the theory of metals. And it states the following, that if you take free electrons as your starting point for the theory of metals, as Sommerfeld did, then you get a Fermi surface, and the volume enclosed by the Fermi surface is just given by the number of electrons. You just occupy all states inside the Fermi surface. But the deep theorem, discovered many years later, is that this volume is a sort of a topological invariant. As you turn on interaction between the electrons, the shape of the Fermi surface might change, but the volume is exactly what it was for free electrons. So this is, how you would compute it for free electrons. And another important feature here is the mod 2. This will be the key thing in all of my discussion. This is simply the statement that when you have a periodic potential, then you have bands. And if you have a completely filled band that does not contribute to the Fermi surface. And here I'm talking about spin 1/2 electrons with no spin orbit, in which case each band has exactly 2 electrons when it's completely filled, and therefore there's a mod 2 over here. Okay, so I'm not going to go to the proof of this. There's a conventional proof of this in every textbook on many-body theory. That's a perturbative proof, which really relies on perturbation theory from the weak interaction limit, even though it sums it to all orders. There's also a non-perturbative proof by Oshikawa, which is, I won't describe that either, which will also be important for things I'll consider. And the importance of the non-perturbative proof, it will tell us, it'll give us a route to violating this relation in a metal. Okay. All right, so but one place where there's already a highly non-trivial application of this theorem is in the Kondo lattice. So we like to think of the Kondo lattice as a bunch of spins. Let's call them the F electrons in some material. So, and if there's no broken symmetry on this lattice, then there's exactly 1 F electron per site. So that's the density of electrons. And then you have some conduction electrons, we'll call them the C electrons of density P. And so the total density in this system is 1 plus P. And if you apply the Luttinger relation to this system, you would say that it should give you a Fermi surface whose total volume should be 1 plus P, which might seem rather strange because these electrons are completely localized. They're not moving. They're just only the spin is rotating. But eventually they did come from electrons that were moving with the Hubbard U. You localize them. But the theory says that no matter how large U is, the volume should be 1 plus P. And indeed, that's what's observed in many, many materials in the heavy Fermi liquid phase. You get a big Fermi surface called the large Fermi surface, which counts both the conduction and the F electrons. And if you want a simple wave function for this, you see that you say, well, let's just ignore the fact that the F electrons have a strong repulsion, and let's just treat them as free electrons. This is effectively the starting point of density functional theory 2. And then you just make a Slater determinant of some hybridized combination of the C and the F, and you fill up a density 1 plus P. So that gives you the right Fermi surface volume because you're treating them as free. And then you project. Then you say, well, I'm going to take that many body wave function and just drop all components of it, which has 1, 0, or 2f on any site. And so the many years of theory by many people, including the ones mentioned here, have taught us that this projection in the end is a relatively mild operation. It doesn't change the basic free fermion state you started with. It doesn't change the volume of the Fermi surface. But what it does do is give you a very heavy mass. So this is the origin of the theory of the heavy fermion. The quasi-particle mass on this large Fermi surface is very large. And all of that comes from doing this a bit better using gauge theories, some of which I will introduce shortly in a slightly different context. All right, so these are all things well known about the heavy fermions and very successful in many applications and experiments. Okay, so here, my focus here is on cases where the Luttinger relation is violated. So I'll put an asterisk. So now you're going to get a new state of matter which violates this relation. So by definition, this has to be something that cannot be accessed in perturbation theory from the free electron state. And one such state of matter is what we call FL star, again, Fermi liquid with an asterisk. Because what we'll see is that it can have a Fermi surface which does not obey the Luttinger relation. We use the non-perturbative arguments of Oshikawa to show that there's a loophole there. And if you had some system with fractionalization and emergent gauge fields, then it's possible to violate the Luttinger relation and get a metal which is not obey the Luttinger. In fact, it goes both ways if you follow this non-perturbative argument. Once you violate the Luttinger relation, that's essentially proof that you do have fractionalization in your system. You can't have one without the other. Okay, so the simplest way to see this, and which is what I'm going to describe a little bit more carefully, you just take the same old Kondo lattice and imagine the F electrons, instead of becoming part of the big Fermi C, they form a spin liquid. And I'll discuss that very shortly, what the spin liquid is, with 1 electron per site. And this spin liquid provides the required fractionalization and emergent gauge fields. Then you get what you very naively might have thought first, that the C electrons form a metallic Fermi surface of size P. But that explicitly violates the Luttinger relation. Some other context, this is called the orbital selective mod transition, meaning that it's the F electrons, the F orbitals that are localizing, but the C electrons are not. But for this to be a non-perturbatively stable state, you absolutely do need fractionalization and emergent gauge fields. Okay, so here's the very rough picture of the Kondo lattice. Suppose the F electrons, because of their mutual interactions or induced interactions, try to form this kind of spin liquid, which I'll say much more about shortly, where the valence bonds are resonating. Then you have this exotic FL star phase. Okay, this is not the topic of my talk. I won't go into this, but there's I just mentioned a recent experiments by Jim Analysis group, where they have some evidence for such a state in C and cobalt lithium 5. Okay, but my talk is really not about the heavy fermions, where these things are now, I would say, relatively well understood. But I want to go back to the elephant in the room, which is the cuprates themselves, which, as I'm going to review some of the data now. A lot of the data looks awfully reminiscent of this kind of state, where only some of the electrons form a Fermi surface, while the others form a spin liquid. The big problem, however, the cuprates, is that you're not in the Kondo lattice model. There's just a single band that's active near the Fermi surface. This is not to say that some people, well, we have the oxygens, and so you can put there's a two-band model or a 3-band model of copper and oxygen. That's fine. I mean, that's the very high energy description of the system, the atomic description. But when the dust settles and you look at the low energy states, no one's ever seen more than one band near the Fermi surface. I mean, photo emission on the cuprates has been done tremendous, extensively. There's so much data, and you only see one band near the Fermi surface that's active. So whether that band is made up of copper or oxygen orbitals is a secondary question. I want to just take the bands that are seen and form an FL star state. How can you do that? And this has been the big question in the field, as I'll try to, how do you democratically localize some of the, I'll talk in terms of holes and not electrons, localize some holes and not others, even though there's only one band. So how do you get an orbitally selective Mott transition when there are no orbitals to select from? That's really the question. And so there have been various ideas on this, which I'm not going to review since it's not a historical talk, how to do this. But none of them have really led to a computational scheme where you can actually compute things, in particular, write on a wave function, like you can for the FL star state. I mean, I just wrote down a wave function for you here in the two-band model, 3 electrons and resonating valence bonds on the other. That's a wave function. How can I do that? Can I do something as simple for FL star in a single band model? All right, so that's what I want to talk about. Answer this question. Yeah, so before now I launch into this, my next topic would be to just survey some of the data in the cuprates from many years and really highlight what I think is the main thing that is not understood. But any questions? Maybe this would be a good time to pause. I'm just reviewing basic ideas so far. Yeah. Yes, P.S., go on.
With the recent discussions we had in talk about Seamus.
Yes.
Just yesterday.
Yeah.
She made a very big deal about the importance of do a 3-band model.
Yeah.
And how you really have to emphasize the charge transfer energy in the driver.
Yeah.
How does that fit in with your?
Right. So for the online audience, is Pierce asking how does the fact that Seamus sees a lot of evidence for the importance of oxygen orbitals fit in with this perspective? And I think it's really that we are asking different questions. So I'm not saying that the electrons don't spend a lot of time on the oxygen orbitals. They probably do. And it may well be to really compute TC microscopically, you need the oxygen orbitals. Or to compute the Mott-Hubbard gap, you need the oxygen orbital. I don't deny any of that. That's probably all true. But when all is said and done, and you look at the metallic states in photo emission, you only see one band. No one's ever seen a separate oxygen band anywhere near the Fermi level. The extra, and that band is some complicated hybridized version of copper and oxygen orbitals. What precisely which combination is very important for some of the things Seamus sees. It's not important for what I'm going to discuss, because I want to just focus on the low energy degrees of freedom, say within 1 electron volt of the Fermi surface, and understand the pseudogap. And yeah, so yes.
If that's the case, because electron can spend some kind of oxygen band.
Yeah.
In principle, your FL star
Yeah.
is affected by the oxygen band as well.
Sure.
They could have looked at the pairing of, I don't know, pairing of pseudogap or pairing of the PC, but pseudogap feature maybe also followed by some of the apical oxygen.
Yeah. So the apical oxygen position would determine where exactly what temperature range you get it. Yeah, or in which material do you get it? Why do you get it on the hole dope side and not the electron dope side? These are all questions I cannot answer. I'm going to look at experiments and see what they see. And I take work, I learn back from experiments, as I'm going to now discuss, that there is an FL star state. And then I want to understand, develop a theory of it. Yeah. So, of course, it'd be nice to have a theory of everything starting from microscopics. 30 years later, we don't. So let's try something simpler. All right, so this is the phase diagram of the cuprates. I am not going to talk about the superconductor at all. I'm going to focus on some, so let's say 100 Kelvin or higher, and talk about the metallic states. And it's very clear from experiment that two different types of metallic states around. Today I'll talk about the pseudogap, and Friday I'll address the strange metal. Okay. All right, so if you do photo emission, this is one of the experiments I referred to. In this regime here at the overdope side, you see a very beautiful Fermi surface. And if you just count up the area here, or if you think in terms of holes, you count up the area there, it's exactly 1 plus p, okay? And there's only one band. You can look at the dispersion of this, and you just see one band dispersing through. You never see a separate oxygen band anywhere here, okay? So to me, that's as the level of theory I like to do, that's a one band model, okay? And we want to work in this band and understand what happens as you change P. So you're not changing very much, you're just changing hole density a little bit. I forget what this is. This is maybe around 20%, and you're going down to 10%. And then the photo emission changes completely. What you see are these Fermi arcs. There's nothing at zero energy in this region, which is called the Antinodal Region, near pi 0. So the reason it's called the Antinodal Region is when this goes superconducting, there's a large superconducting gap here, and there's a node in the superconducting gap along the diagonals. That's called the nodal region. So terrible terminology, because I'm not talking about superconductor, but that's what everybody says. Okay. So in this region, there's a gap, but this is not a superconducting state. So for some reason, there's no Fermi surface here, but there's some low energy excitation here in these Fermi arcs. So this, so now, that immediately for theory, if I want to think of this as some low temperature state, with a metal cannot have an arc. I mean, by the locus, the Fermi surface is the locus of zeros, or the poles in some Green's function. And that locus as a function of k has to be a closed curve. It can't just end. So this is just theoretically not even a starter. But there have been many people have thought that just about every theory has a full Fermi pocket, as we call it. And this is one particular evidence by Peter Johnson's group of at least something turning around at the end of the arc to form a full pocket. But this has not been conclusively established. And in fact, I also agree there should be a pocket. And really, we hope that someday there will be experiments that see the backside. And there's a lot of indication from experiments that the main reason, one of the big obstacles here is getting cleaner samples. So that's for the future. Anyway, and this is some of Seamus's and Jenny Hoffman's data from QPI measurements, where they also see this, as you can see here in Seamus's data. You see this Fermi surface at high doping, 23%, which is a perfectly nice large Fermi surface obeying the Luttinger relation, and then some sort of arc. All right, so understanding this arc is one of the big mysteries that is, still open, I would say. And another mystery comes from quantum oscillations. So this, bear with me, it's a little complicated to understand the relationship in the different experiments, but it's not that complicated in the end. So what you do is in these measurements, you turn on a very high magnetic field at somewhere around here, 12% doping. And at those fields, there is no superconductivity. And so those very high fields at low temperature, you see these oscillations. And today there's no doubt that in the regime of these oscillations, there's also a charge density wave. Precisely what type of charge density wave is not clear, but there is in particular, is a unidirectional, bidirectional. People still debate, but there are these oscillations. And another thing that was seen was that these oscillations have a negative Hall coefficient, so that gives you think they're electron pocket. Okay. All right. So this pocket here that Peter Johnson was drawing is a Hall pocket. So there are occupied states on this side and unoccupied states inside. This is an electron pocket. That's what it seems to say. So I think the explanation for this, which is still standing, is the proposal by Harrison and Sebastian that you form this electron pocket in the presence of this charge density wave. They proposed this before these were observed. And so the charge density wave vector is this wave vector here and that wave vector there. Then the electron, as it's moving along from here to there, gets scattered over there. And it goes this way and goes scattered there, and it executes that type of orbital. And if you move these over by Q, you get this red pocket here. That's the electron pocket. Here's a calculation we did, in detail, working this out, and indeed there is an electron pocket. Okay, there's only one, and in fact the most important fly in the ointment here, is that when you actually do a full calculation with the full Fermi surface, which is what you would naively imagine, that you have a Fermi surface which is completely full because of a Luttinger theorem, you get a lot of other stuff. You get other open regions and you get other small pockets. You get a whole mess. And this is true for everybody's calculation. And all this other stuff, which is low energy, can be easily detected in the shape of the quantum oscillation or specific heat. And there's been no sign of it whatsoever. I think the consensus today by everybody, there's only one electron pocket. In this high field state, in the presence of charge density wave, there's only one electron pocket. And there is no theory of it, period. Any theory, well, there is a theory of the electron pocket, but any theory gives you other stuff that is not seen. And to me, this is like the most striking thing that has not been explained. Because it's a very clear-cut experiment. It's all at high fields and low temperatures, at zero temperature, essentially. So you can't say, oh, it's some fluctuating state. There is some state here at high fields, which is a ground state of the system, which has a CDW. But any theory, you cannot think of the CDW, the bottom line is you cannot think of the CDW as just some kind of usual charge modulation of a Fermi liquid. Okay. All right. So, okay, so we want to understand this. And so where I'm going with this is, of course, we're going to propose that there's an FL star state at intermediate temperatures. But as you lower the temperature, there is some kind of confinement procedure, and this CDW appears. So there are no emergent gauge fields in this state in the end, but it allows you to explain why there's nothing else. Okay. Well, these are as clean as you can get. To see see oscillations like this, you need very clean crystals. So this has only been seen in YBCO and the mercury compounds, not seen in the LSCO compounds. That's another problem because the LSCO compounds are much dirtier. So you can't see, quantum oscillations require omega c tau to be bigger than 1. Otherwise, you don't see these oscillations. So I think these are still pretty disordered from a theorist point of view, but these are the world's best crystals, really, from the experimental point of view.
The electron pocket has never been seen in optics, even
well,
in a situation where they believe they have.
Well, you cannot do ARPAs at these fields. It is a 650 Tesla and above is where you see the,
But in the first diagram, you have the CDW without.
That's a yeah.
Just assume
Well, that's a relatively weak CDW. Yeah, that's a relatively weak CDW. When you turn on a magnetic field, there's a clear phase transition where the CDW becomes much stronger and really long range. This is some kind of, I mean, I don't know, looking back at it, we probably wouldn't call it a CDW. It's some kind of, Seamus has many pictures of this. It's a relatively short coherence length density oscillation. But as you turn up the field, there's a very sharp phase transition. And in high fields, you see Bragg peaks. You don't see Bragg peaks in zero field in X-ray and neutron. Okay, X-ray. Yeah. You can correct me. Yes. Right. I think here 2D refers to 2 dimensions rather than bidirectional, which is a separate issue. That's yeah. So that is a problem. That is a problem that yes, so in this. So as you can see from this Harris and Sebastian paper, you need bidirectional CDW, and you're right. I guess seems to be unidirectional. So that is an issue. So in this paper, we said, okay, let's imagine that this CDW is 10 times stronger than that. Would you still get the electron pocket? And the answer was yes. So that may be, but that's another issue that needs to be understood. Yeah. Yeah. No, if you could do photo emission at these fields, we would have nothing to argue about. We would love to see if this, directly tests this proposal. Quantum oscillation, unfortunately, doesn't tell you where this pocket is. Yeah. That's something we're working on. Right now, what we're going to, to give the big picture, we're gonna try to understand these type of results at zero field, at intermediate temperatures, and we're going to claim it's an FL star. And then that sets up anyway. Now we can look at the instability of the FL star to a CDW. I don't have any results to present yet, but my student Maine Christos is working on that right now. She might even be listening. But the basic idea is, once you have this state with nothing, this already has a gap in the antinodes. There's nothing there. Okay, so then this whole issue of Harris and Sebastian doesn't arise, because this pocket is only formed around the piece of the Fermi surface here, and that we agree is there. And if you already put by hand, if you put a gap there, then you're all safe as far as all this nonsense is concerned in the antinodal region. Right. So, and this was actually also implicit in this paper. They said, well, let's just imagine there's only a Fermi arc, and we can build an electron pocket out of the Fermi arc. Fine. But how do you imagine a Fermi arc? That's the question I'm going to address, because that's not a theoretically self-consistent concept to work with. Yeah. So, but the bottom line is that there is some state of matter at high fields and low temperatures in YBCO, which we do not understand. And it could be it's a very interesting state that needs to be understood. And I'm not going to explain it either, but we are moving towards that direction. But somebody asked about quantum oscillations and how clean they are. So this is oh gosh, which material is this? This is there it is. This is the LS lanthanum based material. You can't see quantum oscillations because these are just too dirty. But you can see what's called angle dependent magnetoresistance, where you change the angle of the magnetic field to the plane, and by seeing how the resistance changes as a function of angle, you can deduce features of the Fermi surface. This is not as direct. You have to do some Boltzmann calculation and so on. And what this paper showed was that if you looked at the data, there was again a dramatic change in the data. You can't argue with that, between the large doping and small doping regimes, in where there was no broken symmetry or anything. And in the large doping regime, the fit to the Luttinger Fermi surface was completely fine. Whereas in the small doping regime, if you took these whole pocket pictures here, if you assume the arc was whole, like arc had a backside, then you could also fit the data. Now, yeah, so another important point here is that, this backside here, as far as the quasi-particles are concerned in any theory, it's a perfectly legitimate Fermi surface here. But in photoemission, when you measure photoemission, your measurement amplitude is the square of the overlap between the renormalized quasi-particle and the bare quasi-particle. There's a Z factor there. And that Z factor could be very small. On the other hand, in something like ADMR, where you're not pulling an electron out of the sample, you're just seeing what it's doing in the sample, that factor doesn't appear. So the backside is as good a backside as the front side. It's the same as far as ADMR is concerned. You don't have to worry about it. Anyway, but you can see a picture. We don't know if this is correct, but at least it fits the data. Okay, so right, so all of this data, to summarize then, I think there's a lot of evidence that there's some very exotic whole pocket here which violates the Luttinger theorem at intermediate temperatures. And this whole pocket state is somehow the parent of these electron pocket states at high fields and low temperatures. Okay. So that second relationship I'm not going to discuss further, but I'm going to focus now on the first. What is this state here that potentially explains the ADMR and the photoemission? Okay, so I'll pause there. So that was a summary of life in the cuprates, and at least my understanding of from my view, the biggest thing that needs to be understood, the biggest problem that's out there. Experimental. Yeah. Sorry, localized. When did I say that? I may have misused. Yeah, so in this sense, like here, in this FL star state, these F electrons are localized because their charge is not moving. So here the F electrons are localized because they're only forming this spin liquid. On the other hand, in this state, their F electrons are not localized. They're part of the Fermi C. Yeah. So in the two-band model, it's like, okay, it's not the sense of Anderson localization, but yeah. So it's really the F electrons go, maybe I should use the word, go from being mobile to part of a spin liquid. Yeah. There's a theory for this, and it's actually like a Higgs transition in a gauge theory, but anyway.
So in your picture, then the charge degrees of freedom are basically irrelevant for this. So you just attribute this to spin degrees of freedom and to fractionalize the spin degrees of freedom. And so it's completely different to Catherine's view, for example, that it's charge degrees of freedom that are important for pseudogap.
Catherine Pepin. Well, I haven't presented my picture yet, but
No,
yeah.
but you talked about
You're talking about a single band. Yeah. So I mean, for the Condensed Matter is very clear. I think we all agree what's happening, right? So for the single band model, yeah, I haven't given a picture yet. There's a puzzle here. Yeah, but it's related to exactly what you said. How are you going to?
But then throwing away the charge, just focusing on the state.
Yeah. So there's infinite number of papers that try to do that, including Catherine, and we've also written many papers doing such things. So for the next half an hour, forget all those papers, including mine. I will talk about the recent one. I will give you an approach which I think does it right, finally, after many years of trying. Yes.
Yeah, Professor Subir, can I ask one question? Hello. Hello.
Yeah. Yeah. Sure. Yeah. So this is their picture. This is from their paper, I think. Well, this part of there is something at the back, but if you make the charging wave strong enough, that's not such a problem. But yes, correct. Yeah. Right. I mean, in the actual calculation, you do have to take the reduced Brillouin zone, and which is what we did too. I mean, we did the same thing. Yeah, and this is just the photo emission consequence in the unfolded zone. This is just a picture. This is from a full calculation with the reduced translational symmetry. And yeah, yes, absolutely. They're there. I mean, even in the original paper of Harris and Sebastian, they have lots of other orbitals in every picture, even in the reduced Brillouin zone, in addition to the electron pocket. What I was saying, there could be something associated with the backside. That's not such an issue. But what about if you've got a Fermi surface here, as you will if you start with free electrons coupling to CDW, you will have a Fermi surface there. That Fermi surface can't just disappear because the CDW doesn't really act on them. It's acting over here. And there's always something left over. I mean, I think they said, well, nobody ever sees a Fermi surface there, so let's not worry about it. I think that's perfectly fine. But as we need a theory for why nobody sees a Fermi surface there.
There's a question online from Fermi.
Yes.
What is known about the form of the small electron pocket in CP? Is it also a cylinder or tube along phasing?
You mean I don't know the answer to that actually. It may, initially there wasn't much known, but I think now there might be known. But I don't know how much it disperses in the z direction. I don't know. I think it's probably known, but maybe Suchitsa or somebody who's online could answer. There's been a lot of work in this direction since this was first observed. Yeah, anyway, okay. Somebody answers online, you can tell us. All right, so now let me turn to the theory part of the talk. So this part, I will just do a pedagogical introduction to what is a spin liquid and one very likely spin liquid on the square lattice. So I'll talk about insulators now. And how am I doing on time? Okay, we'll see. All right.
Just before you go on, there's another question online.
Yeah.
From Navinder Singh, who says if we try to map the problem of the transition of 1 plus p mobile holes when p greater than pc to p holes when p is less than pc with heavy fermion materials, then what is the equivalent of Kondo coupling in the case of the cuprates? Will there be a Kondo J in the cuprates?
That is precisely what my talk's about, so I'll come to that. All right, so what's a spin liquid? So if I take a half-filled band, single band with strong interactions, you can get an antiferromagnet. And Anderson proposed a long time ago that you could also get a spin liquid where the spins form singlets and these spins resonate. So this is a new type of wave function because it has entanglement over over all scales, and the actual wave function is not as one state. It's a superposition of an infinite number of states, each of which is labeled by, say, in this simple picture, a dimer covering of the square lattice. So what are some of the strange properties of this state? Well, first of all, this state features fractionalization. So imagine I think of take a boson point of view. We could also get the state for bosons, hardcore bosons in the lattice, where I think of a spin up as a boson and a spin down as an empty site. So only look at the spin ups. So then the singlet is just one boson going back and forth between the two sides. It's a bonding state of the boson. So now suppose I add this boson to this singlet state, then I end up with a state with two bosons, which is both spins up. And these spin ups can move away. And so now I have a single spinor half, which has boson number 1/2. So this state has fractionalization because the boson number, which could only be integers, now has excitations when they're very far apart, which is 1/2. Then as things were more understood, people realized that there's another excitation here. In addition to this boson number 1/2, there's a vortex-like excitation now called a Wison. And one simple way to think about it is you take the wave function that I had before, the RBB wave function, I just put a phase factor. I put a factor of -1 for certain terms, not all the terms. Of course, if I put it in all the terms, I don't have the same wave function. Only some fraction of the terms have a -1. And which are those terms? Well, I take -1 to the power ND, where ND is the number of dimers crossing this particular line. Pick a point and take any line. It turns out where you put the line is a gauge artifact, but where it ends is not. So for example, this configuration is 1 dimer, so that's -1. This is also -1. So that nothing changes. And so you can see that actually why this line is completely fake, because nothing is happening. It's still -1. But if I switch around here, I get an extra -1. That was the resonance here. And now I get a +1. So it's only resonances around the endpoint that change the phase factor and so make a physical change to anything. So this little object is a particle. This endpoint can now move around. It's a particle which we call the Wison, or if you're in the toric chord, it's the analog of the M particle. Okay, so these are two excitations that must be there in the simplest RBB spin liquid, which is now, we call it a Z2 spin liquid because that's what we argued in 1990, that we should think of this phase as a deconfined phase of a Z2 gauge theory. So this is where the Z2 charges are carried by the spin-ons or the integer half particles.
You're at 140 and 116 Gower Street, London.
And the Wisons carry pi flux of the Z2 magnetic gauge field. And the spin-ons can also come in two varieties. And so this whole structure, which was known to us in 1990, is since appeared in the exact Kitaev toric chord many years later. So what about the square lattice? So what happens in the square lattice, in particular, the J1, J2 model? This has been studied a great deal over the years. I think now there seems to be a consensus, at least among these four groups, that there's the Néel state here that everybody knows and loves. And for larger J2, there's also a valence bond solid, but there's a little region in between, relatively narrow, where you do get a spin liquid. And again, the current picture is that it's a spin liquid, which is similar to the picture I've just described, but it also, where the spin-on excitations are actually gapless. All right, so let me now turn to it's a point node. Okay, so let me show you how do we do this. If I was just turning the crank and doing a calculation, how do we how do we construct this? So what you do is you start with the basic Hamiltonian, then you do this parton representation. You write your spins in terms of fermions, with one fermion on each side. So there's a constraint that you have to impose. You plug this in here. You do a Hubbard-Strutanovich transformation, and you get a path integral over these fields P's and Q's, and another field lambda, which imposes this constraint. Okay, so maybe, yeah, maybe I can, since I have an iPad, let's see if I can do this and write this out. So where's my iPad? QuickTime, right? There we go. Let's see if this works. Okay, so you rewrite the path integral as z, which is integral over dq, dp, d lambda of exponential of, you get a minus like a q squared, and you get a p squared, and you get, and then minus the Hamiltonian of the fermions I told you, and then you also get like a I lambda times 1, something like this. And then there's also this fermion, this involves the fermion, so there's also an integral over df here. Okay. And now what you do is you just approximate this, the q integral, the p integral, and the lambda integral by a saddle point. So just going to replace q by some q bar, and p by p bar to begin with, and lambda by lambda bar. Okay. And so then when you do this, you just get some free fermion Hamiltonian. Then you compute the energy of this free fermion Hamiltonian, and you optimize it in some kind of Hartree-Fock procedure. Then you include this q squared and p squared term. And then when you're done, you find the values of q bar, p bar, and lambda, and that's your mean field theory for the spin liquid. Okay, so a lot of this work has been done, and when you do this, many people found that there's a very nice state where you choose the p bars and the q bars, so that this HF is the best Hamiltonian for this particular model in certain gauge is a superconductor. It's in quotes because these Fs don't carry any charge; it just spins. But the Hamiltonian has the form of a Bogoliubov-Dijan Hamiltonian with nearest neighbor hopping, nearest neighbor dx squared minus y squared pairing, nearest neighbor written twice, and second neighbor dxy pairing. Okay, so you get some Hamiltonian, and then you can compute these spin-on dispersions. And what you find is that these Fs have these nodal points. This seems to break a symmetry, but that's just a gauge artifact. Anyway. All right, so that's the mean field theory of some spin liquid, where obviously you're doing many drastic approximations, where you just approximating q, p, and lambda by some fixed values. So you want to do better. You want to look at do the full path integral. No one knows how to do that, but we're going to use a few tricks. But before you start doing the full path integral, you look for other saddle points. So this is the ground state, q bar, p bar, v bar, or lambda bar. Are there any other saddle points around? Well, it turns out there are. And this is roughly what they look like. Here I'm showing you the saddle point on the triangular lattice, or a related model. So you had some q bars and p bars, but you get another saddle point with q bar v and p bar v. Okay. And when you're far away from this x, they have the same value. So when you're very, very far away, q bar is equal to q bar v and p bar is equal to p bar v. In fact, these numbers show you the difference between them. Okay. And when you get close to this point x, they're sort of different. But the most important difference is, again, along this cut. So you pick a cut. It doesn't matter where you pick the cut. And then you find that if you cross this point, if any of the q's or p's cross this cut, they flip sign. So the sign of q bar v divided by q bar is flipped across the cut. And this is very reminiscent of the Y zone I showed you. There's a cut, and this is like a vortex in this theory. Okay, and it's the sign that's most important. Yes. You just pick a cut. And in this theory also, it's very easy to see. It doesn't matter where it goes. The energy will be the same. It will be identical with the same. This is a consequence of, this theory has a gauge symmetry. So Yeah, maybe I'll write that's the key thing here. So that this Q here, you know, you can see what happened. I quit the thing. Oh, I quit it. Sorry. Okay. Okay. Amazing. What was I going to say? Yeah. So I have this term, you know, Qij, Fi, Fj. Well, this is invariant actually under a gauge transformation. Fi goes to Fi e to the I theta I, and Qij goes to Fi. Oh, sorry, Qij e to the minus theta I plus theta j. So that's what the original thing is invariant under. But there's a similar thing for the p's, and with the p's, you'll see that this sign is a little different. But it turns out, and this is precisely my next point, we don't actually need to use this full Z2 gauge, this U1 gauge invariance, because it doesn't lead to any interesting topological excitation. We are perfectly happy with just theta I, we're going to take to be restricted to 0 or pi. And then it's a very simple Z2 gauge transformation. This goes to eta I times Fi. The eta I is plus or minus 1. And that's the similar thing over here. So now I leave it as an exercise for you to check that moving this cut around is the same as doing a Z2 gauge transformation. You can move it anywhere you want by that Z2 gauge transformation. What you cannot change is a flux. So if we take the product of these Q's around this line, that's -1. That cannot change. But if I take a flux over here, that has 0 flux because I crossed the line twice. So only loops which cross the line once cannot be changed. Any loop that crosses the line twice is unobservable because the cut is unobservable there. Yeah. Okay. This is quite easy to see and work out for your own satisfaction. This is a fun exercise to find this saddle point. Yeah. This particular picture is from a paper by Yejin He and is done on the triangle lattice, but you can do the same. We haven't done this particular calculation on J1, J2, but in principle, we're pretty confident it is going to work out. Yeah, well, this is where we actually had a calculation. Yeah, for the triangle lattice. It's a little simpler to do the computer work of the triangle lattice. Yeah. But once you focus on just the Z2 part, it works in any lattice in 2 dimensions.
If you go for the square lattice from the quantum spindictive to the Néel state, what happens with the bosons?
Yeah, well, this is what this paper is about. That's a whole different song and dance, and not well understood. That's not what I don't want to talk about. That. I'm already way over time, I think. But I have a second lecture which can go into this one, I suppose. I stop at 1, is it? Yeah. Okay. Yeah, so I'd love to talk about that, but I'm not prepared to, and that's a more complicated topic. All right, so here the idea is I found a uniform saddle point, which is just the thing with these Dirac fermion excitations. And then I found another saddle point, which is this one. And this, of course, not just one, it's an infinite number because this X can be anywhere. And then I could have a density of these. And so I can get more and more of these saddle points. So what I want to do now is sum over all of these saddle points. I'm going to take these saddle points at many, many, many saddle points. I want to do the path integral, and I'm going to just do it in the approximation. I'm just going to sum over all of these. All right. So that seems like a tall task, but you can rewrite that sum over all possible saddle points of this type in terms of a lattice model. And that lattice model is precisely the Z2 gauge theory. So what you do, first of all, you say, well, I'm not so worried about this, what's happening right at the core. What's very important is the flip of sign far away. So I'm just going to approximate the Q. When I do fluctuations, I'm going to say the only thing that can fluctuate in Q is its sign. So I'm going to introduce this Ising variable, Zij on every link, which has only two values, plus or minus 1. So I'm not going to do the path integrals over Qij and Pij. I'm just going to sum over Zij. Already simplified my life tremendously. Okay. And now I put this in the full theory. I have now this Q gets, P gets replaced by this. So they have the Zij factor multiplying the F dagger IF, this whole term. This remains the same. And, pretty soon I'm going to get rid of the fermions too. And then, I have some fluctuations about this. So I imagine doing some of those fluctuations and getting some effective action for the Z gauge field. Well, now I already know from the gauge invariance I described that this Z gauge field, this Z can only depend on gauge invariant combinations. And those are always basically products of Z's around a loop. So you take any plaquette, any shape you want, and take all the Z's on the links of this plaquette and take the product. These are the only type of terms you will get. And this is precisely the term for a Z2 gauge theory. Then you will also get some time-dependent terms that can flip the Z's. And so that you can, since you want to do a quantum Hamiltonian, you just put an X operator, which can flip the Z's. And so you have a transverse field, if you wish, on every link. So this Hamiltonian is precisely the quantum version of Wegener's Z2 gauge theory on the square lattice, or you can write it on any lattice you want. And so now this is the theory I want to treat, which will now give me some idea of how to do fluctuation about this saddle point. I have a Z2 gauge field. I have this gauge invariance where the fermions carry a Z2 electric charge. And these are the fractional excitations, which carry spin a half. They carry a Z2 gauge charge, and they're coupled to a Z2 gauge field. So the original mean field theory corresponds to putting G equals 0, where the Z's are just fixed in the ground state. And now all quantum fluctuations about the mean field theory is the effect of G. Okay. So as G goes to infinity, you can see you get a confining state. You're not going to have a spin liquid. But for now, that's not my story here. There's many articles I've written what happens when you turn up G, and other people have also written. But for small g, the main point here is what we showed in the 90s is that this whole structure is stable for a small g. So even you do a mean field and it's totally stable, turning on a small g. And that established the existence of the spin liquid state. Okay. And one way you can show it's stable is to just integrate out the fermions and take the pure Z2 gauge theory. And so now the F's have gone. But what are you left with? Well, you're left with this theory, which is precisely Wegener's gauge theory. And this theory has the Wisons. So now you could have an excitation shown here, where you flip these Z's to be -1 along any line you want. And there's a Wison there and a Wison there. Okay. There's also a very important constraint that I pointed out in these papers, is that there's an analog of Gauss's law in this gauge theory, which is that this operator X, product of X's around a point, commutes to the Hamiltonian, and this has to equal to -1 for half-integer spin antiferromagnets. That leads to some very important effects, including the connection to the Luttinger theorem, but let me not go into that. All right, good. Okay, so that's another pause point. I guess here, since the discussions have been going on, right? So okay, good. Thank you for that permission. I do have time. Anyway, so I can pause here for a question. So now what I've reviewed here is the general argument of how some exotic thing like a spin liquid can exist. So this goes back to Wegener's proof in 1977 or something, that if you take this theory it has a stable deconfined phase for small g. We even studied the phase transition in the pure gauge theory and so on. But there's a region of small z where the physics is as if g is 0, where the z's are just fixed. There's very little gauge fluctuations, and you put in some very heavy particle carrying a gauge charge, like a spin-on, it can move. You can only create them in pairs because any physical operator is gauge invariant, so it has to involve the product of two spin-ons. But once you create them, they can free to move far away and get you fractionalization. And what this also shows you is that when you get fractionalization or things carrying free gauge charges, you also get another type of excitation, and that excitation is like the flux of this z. This is a magnetic excitation of like the analog of a vortex. That's why it's called a Wison today. And this flux is the smallest stable excitation to these gauge fluctuations of the emergent gauge field. Okay, and so right. So you have the electric charges, which are the spin-ons, and you have the magnetic charges, which are the Wisons. And this is a stable state of matter, which in the very simplest case describes the resonating valence bond state. Okay. Of course, today there's, of course, zillions of spin liquids with many complicated gauge fields and lots of other stuff, but this is the basic simplest one. Yeah.
Very basic question. So coming back to the Python.
Yeah. Yeah, they do.
And then why is that?
Well, I mean, you could just see it from this wave function here. So right. So we're going to take. So we take the RBB state. So of course this has, in terms of this boson number, you have one boson here, one boson here, one boson for every bond. But the actual state is a superposition of all. So really, the boson number on every site is 1/2. In every state, on average, the boson number is 1/2. Okay. So this is a state with boson number 1/2 per site. So that's the ground state. So any boson number we are measuring now is relative to that ground state. Okay. So now in this state, this object has boson number 1/2 relative to the ground state. And this is boson number -1/2. Well, no, and this is boson number 1/2 because you added a boson. So you added one, that one split to 2 1/2, they can move away. But in here, I didn't add a boson. I didn't add anything. The boson number is still 1/2 on every site, it hasn't changed.
Oh, okay. So that's relative to the
It's all relative to the ground state, of course. Yes, the ground state is a boson number 1/2. I mean, that particular point is actually very. Sometimes that fact that the boson, the ground state also has a boson number is very important, which is what I'm not going into. That's what leads to this constraint in the Gauss law charge. And this is the Gauss law, which actually measures the gauge charge in the background. And it's as if you have to remember that there was 1/2 a spin-on on every side to begin with. And you can see that you see the connection to Luttinger's theorem. You have 1/2 a spin-on per site. It's a 1/2 band of electrons. And that 1/2 doesn't totally disappear. And when you do the non-perturbative proof of the Luttinger theorem, it's exactly this thing that comes in and saves the day. But I'm not getting into that. Yeah, go ahead over there. Then you next. Yeah, please. Yes. Yes. So there is the. Right. Yes. So good point. So first of all, let me just show this here. That's a great question. Okay. So if I remember this, yeah, here we go. So there's this U1 gauge symmetry. Yes, it's broken. Now, this is a gauge symmetry, not a global symmetry. So there's no, so there is no Goldstone mode. There is the massive gauge boson as like in the theory of weak interaction are the W and Z particles, which are what's left over from the Goldstone mode. So here there are also analogs of W and Z particles. I'm just ignoring them because there's some high energy excitations. They are there, but there's not believed to be that important. Yeah, I mean, when I integrate out the fermions, they will give you an action for the W and Z particles. I'm just ignoring those particles, okay? But this theory has, the gate, unlike the theory of weak interaction, where the gate symmetry is fully broken, here the gate symmetry is only broken down to Z2. And so there's still some residual gate symmetry left. And now normally, when you have like a U1 gate symmetry, you have a photon, but this is a discrete gate symmetry. So you don't have a photon, but the analog of the photon is the Wison. This Wison is what's left over of the photon in the discrete gauge theory. Okay. So this Wison this carries flux. I mean, that's all. Yes, I think I did answer every question. I think I did. Okay, yes.
Starting from this single band theory, and you have some spiral system, the negligible something you can imagine trying to solve the problem by going to the basis in which you have like paramagnetic interface.
Yeah, you go to rotating reference frame.
Yeah. Then we can imagine having an expanded like two-band model with like electrons.
Yeah, sure.
In spiral, and then you might imagine that you could actually have sort of a fundamental phase, and that then you can have Fermi arcs and maybe also quantum oscillations. So I just wanted to hear you, smack this down and tell me about the problems are. Very nice.
Well, I mean, in Weyl semis, the Fermi arcs are only on the surface. We have Weyl nodes on the bulk, and you have Fermi arcs on the surface. So Fermi arcs are possible on the surface of a three-dimensional crystal, but that's not what we're talking about. We're just talking about a two-dimensional layer on its own. So it's not on the surface of something else. So we can't use that mechanism to get Fermi arcs. What happens there, when you have Fermi arcs on the surface, you get an arc, but it doesn't end. It actually goes into the bulk. It connects to a band in the bulk. So here there's no bulk to connect to. So we can't have an arc. The other question I thought that occurred to me, suppose I want to now dope a spin liquid, and I dope it the way you're suggesting. You go to some rotating reference frame, put in some charge carriers in the rotating reference frame. We've written several papers on that, that you can go with that a long way. But what you find then is if you get these fermion charge carrier in that approach, those fermions carry charge but no spin. And so they will not show up in photo emission as an arc, because in photo emission you're ejecting a particle that carries both spin and charge. So that also doesn't work that well. I mean, you can try to fix it up, and we and Wen and Lee and others have tried to fix it out. Anyway, so there's been a lot of these attempts, and hopefully I'll convince you by the next half hour or 20 minutes that these all have a Rube Goldberg structure, and there's a much simpler way to do it all. Yeah. Well, including the discussions, right? Oh, including the discussion I ended one. Well, then that'll have to be postponed to the next lecture then. All right, fine. Okay, so let me just, all right, so that I'll keep you in suspense. Next lecture, let me at least do part 3. Okay, so let me just go back now to the Condensed lattice and just talk about these two phases of the Condensed lattice in a kind of a gauge theoretical way. So we start with the Condensed lattice, and how do we get an FL star phase? Well, we just say that these Heisenberg this part of the Condensed lattice forms a spin liquid, and so here's my Hamiltonian for the spin liquids. Here I just totally approximate and even throw out the Q's, only keep the P's. So I just have some free fermion Hamiltonian for the spin liquid, for the F's from here. And then I have the conduction electrons, which is, this is the same thing written out here. Okay. So there it is. That's my Hamiltonian for the FL star phase. I have a small Fermi surface of the C, they form a stated determinant. And for the F's, in this approximation, I just take free fermions without even pairing. So this is actually U1 gauge theory here, not a Z2. So I get stated determinant of F, and then I project onto one F per site. Okay, so that's the FL star state. Okay, and all right, so now what about the large Fermi surface state? Well, in large Fermi surface state, you include a hybridization between the F and the B. And now what you see is that this F carried this gauge charge I was just telling you. So for this thing to be gauge invariant, the B also carries a gauge charge. So this B is like a Higgs field carrying a gauge charge. And when it condenses, as you know, this is a single elementary Higgs field with unit gauge charge. So the gauge, there's no Z2 left over. It's just the gauge symmetry is completely gone, just like in the weak interactions. So this is it. This is the, you know, the slave boson condensate, or the Higgs field, which breaks the U1 gauge symmetry of this part. And so you just left with a hybridized band, and you obey the Luttinger theorem. So in this point of view, this state breaks the Luttinger, it does not obey the Luttinger theorem. And this must mean there's some emergent gauge field, in this case U1, or it could be Z2. So that's what's required. When you break the Luttinger theorem, there's a gauge symmetry left over. When you get rid of the gauge symmetry, then you have to obey Luttinger theorem. And indeed you do. Okay. All right, so 2 minutes. So let me just give you a preview then of what I mainly wanted to talk about. So how do you do this in a single band model? All right, so I'll just give you the answer, and then maybe many of you will figure it out by the next time. You start with the Hubbard model, and then you do the very familiar thing of decoupling the Hubbard interaction with the spin squared term. And so this is an exact representation of Hubbard of this interaction term. It's an integral over some Hubbard sandwich field phi, which are now called the paramagnon, which is coupled to these fermions, which are otherwise free. Okay. All right. And this particular theory is the starting point, you know, of variations of it, starting point of superfluidity in helium-3, of and of the entire D-wave superconductivity theories of Scalupino, Pine, Shubakov, Schmallian, and many others. Okay. So what I'm going to do different from them is I'm going to try to write a Hamiltonian for this phi. So this phi on its own is some spin 1 excitation, which is gapped, which is sort of damped out by the coupling of the fermions, but let's ignore that for now and just think of it as some gapped spin 1 particle. So I'm going to create that particle by adding these ancillar spins, 2 layers of ancillar spins with coupling J-perp. So on their own, they like to form spin singlets, but now they have this gapped excitation. And I'm going to identify this excitation of phi with the excitation here, with this phi here. Okay, so my claim then is that this model here of my original, so I start out with the Hubbard model. I'm just rewriting the Hubbard model as free electrons coupled to 2 layers of spins. Each of these form a square lattice with a coupling J-perp. In fact, there's a Schrieffer-Wolff transformation that can take you between these two. This theory here is completely equivalent to that theory after a canonical transformation. This theory has a paramagnon on these spins. Okay. So these are ancillar degrees of freedom that I introduced to make life simple for me. And even in quantum computing, why do we introduce ancillars? Well, we introduce ancillars because they allow us to write down states or create states of the physical qubits that you're looking at with complicated types of entanglement. So here we have these ancillas, which we're now going to use, put to good use to get complicated entanglement on the physical degrees of freedom, including a state that's an FL star state. Okay, so I think I've told you enough to figure it out. Yeah. Okay. So exercise for next time is create an FL star from this 3-band model. Okay. All right, thanks.
Schedule lunch. Proposal here, and the focus here.
Okay. Friday. Yeah.
Thanks very much.
Very much.
You're welcome.
I didn't know that was a big cool trick.
Yeah, it works pretty well, doesn't it?
Yes, I could.